So first, a little background about GeoMesa. It's a collection of libraries and modules that let us solve the problems that we're trying to address here. So you can pick and choose. You don't have to grab a big system. You don't have to necessarily deploy Accumulo. That's what we're going to focus on today as we talk about it. But you do have some options for solving your pieces in a composable way. Whenever you talk about geospatial data, there are two broad categories. The first is vector data, where you have points, lines, and polygons. It could, describe the road network, where events happen. It could be the outlines of buildings. Those would be great examples. That's what we primarily focus on. There are other projects that handle raster data. An example of that would be imagery that's coming off of the Landsat satellites, or other overhead imagery, or map tiles that you've rendered from vector tiles. And the great thing about GeoMesa, it's open source. We're building on top of other open source libraries like Accumulo. We also work with other Apache projects like Kafka and Spark to help us get streaming capabilities and other distributed computation. And there are a number of geospatial libraries that we pull in, like GeoTools, and we have ways to work with GeoServer for some of the capabilities there. One of the great things that we can get to, Russ indicated this a little bit, we can build up complex architectures that are based on Accumulo here for the sort of batch layer in a Lambda architecture. The speed layer that we might want to talk about, and for some of the near real-time processing, we actually do that in Apache Kafka usually. And as we get to the right-hand side and get to client access, that can go through a product called GeoServer, which speaks all the open source protocols that your web browser would speak whenever it's using a JavaScript library like Leaflet. This gives us a chance to make a request that could be going against a live layer, an in-memory database that's populated from data that's continually updating, and switch over to making a historical query that is interrogating billions of records in Accumulo. Okay, so let's talk through a typical use case that we might have for GeoMesa. The first thing that we have an ETL converter library capability that's going to help us get data into the system easily, so that whenever you bring your mission data, your particular data set you're interested in working with, we've got a way to transform it into records that GeoMesa can work with. For a data management and streaming capability, we have integration with NiFi and Kafka. NiFi lets you handle flow files, and that's going to give you a chance to understand how data is moving around in your enterprise. The Kafka data store lets us use Kafka as a write-ahead log to say where messages, where they're landing in time. We can put several of those together to build up complex processing. One example that we can do with this easily is implement some sort of like geofencing. If we were tracking something, we could see when our vehicle moved in a region, moved outside of a region, and alert appropriately. Accumulo, which we'll focus on in a minute, we're optimizing that so that we've got fast query returns so that we can have interactive data analysis. With Spark and Jupyter, that gives us a chance to also do some interactive analysis, data discovery, and get to see what our data, what's going on there. Okay. If we put this all together, we get speed, as one of the founders of CCRI is noted for saying. We can get to what we're looking at, we can discover new patterns in our data, and do some really great things with it. Okay, so that's the background of what GeoMesa is. In this talk, I want to kind of say where we are in our life cycle and what we've had a chance to learn about as we've worked with Accumulo over the years. We're on a journey, so to speak, here. And there are some things that we got right out of the gate, and there are things that we've iterated on in the 2.5, 3 years that the project's been an open source project. So I wanted to talk through that maturation that we've done. The first part of it, we're going to talk about how we actually store the bytes in Accumulo key value pairs. And that means we have to talk about space-filling curves and a little bit about how you're going to index multidimensional data. After we've done that, we're going to talk about using Accumulo iterators. I don't want to claim to be an expert on this. Russ has already said that an iterator stack gives you a lot of power, and I think this section is going to end with an appeal to go to Josh's talk to see the new testing framework there. We can do a lot with those iterators. We can't do everything. That's the last section where we talk about using MapReduce, using Spark, and plugging into some of these libraries or notebook servers that are becoming popular to do data discovery, see what you've got, and interact with it. So there are some things we don't get to talk about. We don't get to talk about this sort of distributed real-time processing that you can do with Storm and NiFi. There's this live view with the Kafka data store, getting data in and out, using command line tools, all of those things that make this an easy-to-use product. We don't have a chance to talk about that, and there's some other analytics that we'll skip over. So this is not the State of GeoMesa talk. This is the State of GeoMesa on Accumulo talk. All right. So as we talk about how we've worked with schemas, the first thing we need to come to terms with is how query planning in an Accumulo-based system is going to work in general. And our traditional application is going to have some requests that get made to it, and there's going to be a moment when we have the query. We've written, the big SQL query, or it's been generated based off of the user request, and so there's a step from OpenLayers and GeoServer that's talking to the user down to the database. Here I've got PostGIS sitting on top of Postgres. This is a typical open source geospatial architecture that you would have. OpenLayers is this JavaScript library, runs in your browser. It can talk to GeoServer, and if you're talking to PostGIS, it sends out the query, and Postgres has a great query optimizer, great query planner. It's going to tear apart that query, use your indices, go to town. With what we're doing in Accumulo, the query plan for Accumulo is very basic. So we're going to actually need to have a scan plan for how we're interacting with Accumulo. So that query planner kind of gets pushed up into the application level. So everything we're talking about from here on is how do we build up a key structure so that we can have an efficient query plan. Okay, so as the introduction mentioned, I work on a few projects. One of them is called SFCurve. That's about space-filling curves. I'm a mathematician. There's a lot of fun stuff. If you feel like I haven't said enough about space-filling curves, I'll be here for the rest of the day. So I'm going to try to keep this to one slide. There's a lot of cool math here. There is some, I think, legitimately novel things that we've figured out as we've worked with Accumulo and worked with some of the other projects about how space-filling curves compose. That said, this is the crash course for the non-mathematician. Our goal is to index multidimensional data. If we have one-dimensional data, Accumulo provides a one-dimensional index. You just put it in that, put it in an order, and you're off to the races. Two-dimensional data doesn't have an a priori one-dimensional ordering on it. You're stuck. We've got to do something. So this is when you'll hear people talk about using GeoHashes, space-filling curves, and so on. So we're going to have a few steps. The first one, and oh, sorry, this is not rendering well. We've got a grid that we're going to put on our spatial extent. So the grid is actually a regular grid here. It looks like it is not coming through well in the PDF. Okay, that one hopefully will give a little bit better idea of what's going on. Once we've gridded up our data, we're going to use one of these space-filling curves to indicate what order the cells are in. Once we've got that, we've got an index. We can start in the lower left corner, say everything that's in this 1/64th of the world is labeled with a 0. Move over one cell, it's a 1, and so on, 2, 3, 4. We've got a label for everything we're talking about, and that gives us a byte representation. So this is a GeoHash scheme, or you can call this a Z-order curve. Just for context and reference, I'm going to call this Z2 because we can also have a higher dimensional analog, Z3, that takes 3 dimensions. This is the space-filling curve you would have invented if someone came to you and said, index geospatial data. This actually happened on the user list. Someone wrote in, I think it was a year and a half or 2 years ago, and the conversation started, hi, I want a lexicoder for geospatial data. The third or fourth person that wrote in said, I've got a great idea for you. Take the bits from longitude and latitude and just sew them together, interlace them. That's exactly what this is. So it's really easy to calculate, it's really fast. So the one bit of text that I skipped over is that we do want to have some notion of good space-filling curves. They're going to be recursive, which means that if I stop my bit representation at some point, I'm going to indicate a kind of bigger block. If I keep going, I'm going to keep chomping that block apart and carving up a smaller space. There's also a notion of locality, where we want things to be as close together as possible. This is okay in a Z-order curve. If you wrote down a row major or column order, a row major order curve, it would look a little bit worse. Okay, so no one's asking for all the data exactly on these artificial divisions that we've made as we're splitting the data up. So a query range region that comes in is actually going to touch multiple blocks. As that happens, we can filter that out on the, with the Accumulo iterators, or the other option that we have is to go ahead and return all the data even though it's a little bit more than we want. That gives us a chance, if we've got something like GeoServer that's going to be producing a final visualization, taking that extra data, it's not going to get written to the tiles that are returned to the screen. So that kind of loose bounding box is a typical trick in PostGIS and other products. So just to chat through one of the actual table designs we use, this is our Z3 table. It's designed to work for point data, so we're not talking about lines and polygons, and we're also storing one piece of temporal information. So the 3 dimensions are longitude, latitude, and time. What we're going to do is we are going to use 1 byte to have a little bit of a shard in Accumulo. This gives us a chance to spread data around in case there's any hot spotting. We've got a little bit of room there. We only usually use 4 splits there, but we've got a little bit of room for some options there. The next thing that we do is this shows an example of using a week-based epoch, or week since epoch. What that's going to do is by the time we've used the next 2 bytes, we're going to be, all the data beyond that is going to represent data from 1 week. So now, if we're making queries that are for a day or 2, we're inside that week, we're drilled down pretty well. If you were making queries that were longer, you would want a different sort of range here. We can split the time up into this week since epoch, and we can also split it up into the seconds inside of the week. If we take that seconds inside of the week with the X and Y, we're going to use this 3-dimensional space-filling curve Z3. That gives us the next 8 bytes. We're not worried about doing anything fancy with column families or column qualifiers here in this example. So those are empty or just kind of as bare as possible. And for the value, we're just storing serialized, the serialized record. So if we wanted to calculate for here and now, that's the worked out example below. So we can get this representation of where this talk is right now. Okay, the one thing that happens for non-point geometries that I want to touch on briefly is we have to work out where to store things. If we were lucky, we would pick a resolution and we would have geometries that were small enough that they'd fit inside the boxes that we've decided for our grid. And if that happens, we're done. We don't have to think hard. If we move one of those boxes, even if it's really small, it might cross one of our grid boundaries, and we'd have to make some choices. The easiest approach is to just say, I'm going to cover my Nonpoint geometry with the grid cells. That runs into some problems, and the first of which being that you need to store the data multiple times, so you have to deduplicate it. So a handful of researchers, this is where this continues to be a journey. A handful of researchers from 1999 had written a paper where they say, hey, let's go ahead and explain how we could get around this. And the key idea is that you're going to pick the bounding box for your Nonpoint geometry. You're going to pick its lower left-hand corner, store it by that one time. And there's a little bit of a size separation that you set up in your indexes so that geometries of different sizes are segregated. After you have that separation, there's a little bit of a trade-off on the query side. You have to think through what to do there. And so as you ask the different levels, you have to fiddle with the query box a little bit. But it's worth the trade-off since you can save on deduplication. Okay, let's talk about iterators. And again, this is most likely, as I said, the advertisement for Josh's talk in the next section. Okay, so Webster's Dictionary reminds us what iterators are. I mean, the Accumulo documentation. The key idea here is this is how we're going to push down what computations we want the tablet servers to do. And the key idea of their modularity is they can be stacked together, composed, remixed, and you feel like you're really off to the races. So one of the notes, and I'm sure the test harness will help work this out, one of the notes is that these work on sorted key value pairs. If you violate that contract, you will be punished. So, and the iterator code, thanks to some great improvements, can be loaded from HDFS, and they can also be namespaced. Back in Accumulo 1.5 or 1.4, before that was a possibility, we constantly were messing with each other because we were sharing one or two clouds, and if someone said, oh, I want to try out my new iterators, it meant no one else's stuff is going to work. Okay, so let's talk about our motivating use case for why we'd want to push computation down or move it around in the cloud. So if we don't have any way to improve our visualizations and we just get back our data raw and then show it to someone, we might pull back all the points for shipping traffic that's happened in an area like the Mediterranean. Even if we do a little bit of styling where we maybe label each point a little bit differently based off of our favorite sort of neon green color, we get to a point where the data doesn't really make sense. We see that there are a lot of ships. So for reference, Greece is kind of right here in the middle, and it looks like a big mess. If we can generate a heat map, we can start to see where the shipping lanes are. We see where there are some really high throughput areas, and our data starts to make sense. And the great thing about this is it's faster to get this picture than it is to get the other one. Part of the reason is because we can push down that work for aggregation all the way down to the tablet servers, use iterators, and send back less data that needs to be aggregated by GeoMesa and then styled by GeoServer. So the idea here is that our OpenLayers map client, as it makes the request to GeoServer, it says, hey, don't show me nonsense, show me a heat map. GeoServer actually turns around, subs out that style that happens, makes a request called a WPS that GeoMesa knows how to interpret. That lines up query hints as those get passed down, and that changes the scan plan in Accumulo, and we configure iterators to do it. Okay, so this should give us an idea of the two steps that happen whenever a request is made to GeoMesa. First, we've got a request for some data that we want to visualize, style, get back. That's the first part. We can filter it. We can do that by spatial bounds, temporal bounds, attribute bounds. We can really drill in and say, this is what we want to see. The second part of the request is, how do we want to see it come back? Do we care about seeing the full features? Are we going to be looking at a tabular view of our data? Or do we want some sort of aggregation, whether it's a histogram or a heat map? Okay, since we've got these separate concerns, this gets us off to the races. We're thinking, gee, I can solve this problem by picking with our space-filling curves which ranges to scan. That's going to do some of the filtering for us, because if we're using a table with a spatio-temporal index, we'll be able to restrict to only things in a particular region or particular time by the scan. We can have a filter that cleans up the rest. If we're trying to apply a more complicated filter, maybe we could have another iterator. And for the transformation, we could have one more. And whenever we wrote the first paper describing how GeoMesa worked, my colleague Chris Eichelberger put together this great drawing that shows, okay, this is the stack we're going to kind of see. We've got all this data on disk at the top. The Accumulo system iterators apply authorizations and visibilities, so some data drop out. If we apply the geo index, we can have an iterator that takes care of that. A few things, make it further. We can apply that final filter, give me exactly what I want. And you could imagine stacking on top of this iterators for analysis or for aggregations. Okay, that was a great idea, and the key benefit of it is you can explain that to someone really well, and you've got pieces that you can remix in a modular way. The downside to it is you wind up doing the same sort of things where you're serializing and deserializing data between the iterators. So jamming it all into fewer iterators works out well for us, and that's one of the things that we've moved to. So the code winds up being a little bit more complex, but it's faster. So that's kind of one of our first lessons learned. One of the other cool tricks you can pull, if your serialization, if your data allow for it, you can do a little bit of a lazy load or evaluation where you don't just read your values, turn it into a Java object, and then apply whatever filtering you need to for that. You can sometimes pull things out of the value and work a little bit quicker. As I already alluded to, don't lose time trying to debug your iterator if it's not returning sorted keys. You're doing it wrong, and there will be pain and suffering. And I hope there are other cool things to learn about in the test harness. I haven't had a chance to look at it yet, but I'm excited. Okay, so far we've talked about how we're using keys to organize our data on disk so we can get to just the data we're looking for, and iterators so that we can transform it as it comes back. There are times when this works great out of the box. For the times whenever we need to understand it a little bit more, we've written ourselves a query plan explainer. So this is just like having Postgres's explain or explain query. The great thing that you can see here, we hand over, this is an example of using it from some of the command line tools that we have. The great thing you can see here, you immediately see what hints we've got set. We're not asking for any of the aggregations, so they're all set to none. We can see what strategies were considered, see that it picked up that it was an attribute. GeoMesa has attribute tables, and the query is going to actually use that. We can see what tables we're going to use and what ranges we're going to set up. And we usually get an output that tells us how the iterator is configured. So that way, you could just interrogate a system and say, how would you run this query? What's going to happen? In the off chance that things go really off the rails, you can also see how long the planning time is. This gives us a chance to make sure that we're not calculating a million different plans for a query. All right, so in the final section, we'll talk about GeoMesa's Spark support and a little bit about using it with notebooks like Zeppelin and Jupyter. Okay, if we talk about what we've done with iterators, If you were a big MapReduce guy, you would say, gee, if I've got MapReduce, I could go ahead and do the same thing. I could map over the data, reduce it into a histogram or heat map. Great. You've got tasks that work as kind of one map task and one reduced task with iterators. And so putting that online is a big win. That can go straight back to the client. If we want something more complex, we want MapReduce. Okay, Accumulo's got MapReduce input formats. We're off to the races. And Spark has a way that if you have an input format, you get an RDD. So if you go ahead and just have a little bit of glue code, and if you can manage your class path, you're great. You're off to the races. So just as some quick examples, we can build up a time series of our data. Our first step is to fill in the pieces that get us an RDD of simple features. And then the second step is to actually calculate a time series. And this was done by one of my coworkers who evidently doesn't like ggplot. Our second example, and this was worked out by our intern this summer at Tala, instead of sort of reducing by a day or a date, we reduced by regions. So we needed to pass around spatial information. Here are the outlines of the countries of the world. The data set behind it is GDELT, which has over 200 million events that all relate to how we interact with each other in the world. So we're aggregating some of those records by country and then analyzing the Goldstein values as some sort of proxy for stability. And this was this was run on data from about the time when Russia was messing with the Ukraine. So the next example is pretty much the same. We could go ahead and look at how tweets about traffic work in Virginia. So where are people upset about their traffic, or at least saying something about their traffic? We can go through the same idea of taking the counties in Virginia, distributing them around the cluster, and then pulling back the tweets for each county and counting them. Okay, so as a small note that came up along the way, a developer came by one day, he had written a Spark job, and he said, why does my Spark job have thousands of tasks in it? And some of the guys who work on GeoTrellis, Eugene, wrote into the user list about the same time and said, hey, I'm seeing thousands of tasks in my Spark job. And it turns out that in Accumulo 1.6, every range that you set up in a query plan actually becomes a MapReduce split, and then those become Spark jobs, Spark tasks. So that's just one of the things that we've had a chance to understand a little bit better, and we've written input formats that try to help pull some of that back together by tablet server. Okay, the thing to wrap up with is where's this going? And it's not just enough to store the big data and be able to run a batch job that comes back in hours or minutes. We need to have a way to dive into the data, understand it, and work with it in a live way. Also, writing MapReduce in Spark is pretty error-prone. It takes some time, it's pretty challenging sometimes, and it can really sap the life out of you. So the answer to this is these notebook servers like Jupyter and Zeppelin. Okay, there's already Spark support, Spark 1 and Spark 2 support for Jupyter. So again, we're down to if we line up the pieces so that we can see the visualizations in the notebooks, if we line up the class path, we're going to be off to the races. And we've had a chance to work some of that out with GeoMesa this summer. So some of the future steps there's more to be done with JavaScript. Zeppelin has some nice graphics that you can, or nice interfaces for tabular data that you can just remix. Having some interactions that go between a map and a histogram is going to be something we're looking at. OpenLayers is one of the libraries I've mentioned several times. There's also a library called Leaflet. Working those things out is kind of, on the map. Jupyter started out life as IPython notebook, and a lot of data scientists really don't want to learn Scala. Can't blame them. They already know Python. So if we provide Python bindings for projects like GeoMesa, it's going to make it easier for people to interact with their data. Okay. With that, I'll open it up to questions. So the question is, as we were collapsing the iterators, and correct me if I don't paraphrase it properly, as we collapsed the iterators, how did we do that, and what sort of ways did we understand what was going on? And this is one of the, since it's happened over the course of, 2 or 3 releases of GeoMesa and over 2 or 3 years, I don't have the one chart to show you to say, okay, old way, new way is 10 times faster. One of the things that we could see is if we go back to this kind of picture, if we wanted to apply this filtering, we might wind up reserializing our data as a Java object 2 or 3 times. And so this was really kind of one of those things that happened at that hunch level where we're like, wait a minute, if the thing that we do is if one iterator looks at a value, opens it up, turns it into a record, chomps on it a little bit, says, okay, I've calculated the projection for it, or I've filtered it, packs it back up as a value to pass off to the next iterator that looks at it and says, I only want the geometry out of it, packs that up and sends it off, we've lost a step there that we could, we've got one extra step of indirection. As we made those changes, we were able to implement effective benchmarks at the time that showed us, okay, we are going in the right direction here. Good question.